Okay, the last topic. We are now in topic 17, oscillations. We define what is simple harmonic motion. Right? Acceleration is proportional to displacement from fixed point and is always directed towards the fixed point. Summarized by this equation. This one you have no choice. Memorize. Right? Either directed towards that point or acceleration and displacement are always in opposite direction. Either one. Then we say that right? This is a solution. This is a solution of differential equation. You can differentiate two times and then you'll get it back this way. Not required for us. Okay, so that sine curve tells us that the, the oscillation starts from rest position and moving to the right. Okay, so let us, this one is more popular. Example 17.1 show that for small angular displacement, theta is less than 10 degrees of the bob of pendulum, so that the motion is simple harmonic, and the period is given by d is 2 pi square root over L over G. Right? All we need to do is show that acceleration is proportional to displacement. That's all we need to do when you are asked to show is simple harmonic motion. Okay. Right? Remember, natural frequency is just F naught 1 over T, one of the period. And we are, right? That's what we have been using in your SPM or O level. Right? This is the rest position or equilibrium position. When the angular displacement is less than 0 degrees, the arc length, that distance, that arc length is approximately the horizontal displacement. Approximately this one, horizontal displacement. And if you look at this as a circle, then this becomes theta is x over L, where L is the length of the pendulum. And then we proper derivation, we use theta equals sine theta equals approximately equals tangent theta, because it's 10 degrees. We can use that. Derivation, and we displace it. Displace this is a string, is the bob. Displace it. Displace it slightly. When the bob is displaced, when the bob is displaced to position B, the forces acting on the bob is the weight W and the tension T. Okay, what are the forces acting? The weight of the bob acting downwards. Tension in the string D. Okay. So resolving the weight in the direction of the tension. Right? That's your D. That's your W. This is theta. So this is also theta. So it's W cos theta. Okay. Remember, this is supposed to be horizontal, right? Because the angle is small. But these two forces balance. So this is the resultant force. W sine theta is the resultant force. Okay? So resultant force F equals W sine theta. So the direction, the resultant force is in direction of minus x. Right? It's to the left. So it's in direction of minus x direction. So we are going to use that substitution. Right? Arc length is r theta, or in this case, we use x, that distance there, x is L. L is the length from the suspension to the center of the box. Theta or theta is x over L. Right? Using Newton's second law, resultant force is MA equals to mg sine theta. Right? Negative because we take to the right as positive, so it's going to the negative direction. So for small angle, theta in radian equals to sine theta. And then we replace sine theta as theta in radian, x over L. So we get A equals to minus G L over X, where GL is a constant, G is a constant, L is a constant. So in this case, we have shown that A is proportional to minus X. Right? So the motion is simple harmonic. Okay with that?
Yeah.
Okay, now we derive this equation. Right? We have obtained this equation showing simple harmonic motion. Then we compare with the definition. There's a definition, right? Omega angular frequency is a constant. So compare this omega square equals to G over L. Omega square is G over L. So T is 2 pi over omega. Same as circular motion, right? 2 pi. Then we get this one. Okay, with that or not? Any comment?
Yeah, so
Yeah, okay. Variation of velocity and acceleration with displacement. Right? We look at the definition. Compare with the equation of a straight line. So this is the equation of a straight line with negative gradient. Right? Gradient equals to minus omega square. We just sketch that out. Right? X naught is the amplitude. Minus x naught is amplitude also. So A naught is the maximum acceleration. So that's the equation of a straight line passing through the origin with the negative gradient. Stop me, we need to ask question. Right? For velocity, we just refer to the graph. Right? Velocity doesn't matter where you start. This is the equation. This is the equation that's given in the formula sheet, or you can use a table. So the first point, x equals to 0. X equals to 0 is v naught. And at x naught is 0. And is 0 minus v naught minus x naught is 0. So usually you won't have funny shape like straight line, straight line, straight line one. Right? It's either a circle or ellipse. But usually we draw it as ellipse because these two distance are different. Okay, this is the equation of ellipse. Where this is A, this is minus A, this is B, this is minus B. If A equals to B, then it's a circle. You don't need to go to all that detail. This is just for your info only. Right? This is also your for info, it's not in the syllabus. Right? To show that this is just for you if you are interested, right? To derive the equation. Usually A-level physics, there are certain derivation you need to do. They don't want to play you down with all the derivation because it's unnecessary. So this one, if you want, you can derive yourself. Won't spend too much time. And to show you the equation of the ellipse, right? We are just using this equation, squaring it, you get that equation. and take this one over, right? Then divide by omega square x naught. You get that? I know in the syllabus for your info only, for your our curiosity. Okay, you won't bother about all this also. Sufficient to know how to get this straight line. Know that it's an ellipse. That's all. Okay, the ellipse can be vertical. It doesn't have to be horizontal like that. Right? It can be vertical. Okay, any comments so far or any question?
No, it's okay.
Okay, let's carry on then. Relation of displacement, velocity, and acceleration with time. You can either use this one, or as I said, we have derived the equation. We have said that the equation is you can plot it out lah. Right? But we have said that it's a sine curve. Right? You won't have this type of graph like that. Right? So it's a sine curve. Okay, sine curve, as we have said earlier, right? A sine curve. And it's starting from the rest position. Right? So this is a displacement time graph. Then velocity time graph, the same thing. No? You can either use this table or use the equation that is given in the formula sheet. Sorry, jumping around. Okay, that one there. There's the equation of the box starting from the rest position. Right? Forgotten, build a table up and then draw it from the table. Right? Amplitude doesn't count. They may be the same, they may be different. V can be smaller or X can be smaller, it doesn't matter. It's just a sketch you need to show you their relationship. Okay, can use this table to sketch the graph, or since we know it's a cost graph, there's your V naught, okay, it's a cost graph. You cannot compare the vertical scale. This is V, this is X. Right? Cannot compare. What's the phase difference between velocity and displacement? This one you must know. Yep. What's the phase difference between velocity and displacement? This in terms of angle, this is 0, is 90 degrees, right? Or pi
I
over
think
2
it's 90
radian.
degrees.
Okay,
90 degrees phase difference.
90 degrees phase difference or pi over 2 radian. Right? This is a displacement time graph. This is a velocity time graph. Acceleration. Acceleration, you can refer to your definition. No? So what's the phase difference? Pi radian. No? Memorize these two. Pi radian. So it's if you got displacement time graph, the black one, then it's just inverted. No? Inverted the blue one. Okay with that?
Yeah.
Okay, it's just repeating there. Amplitude is constant. The key for displacement time graph is the amplitude is constant for simple harmonic motion. right? Amplitude is constant with time. Right? So usually textbook or this one is obtained from the internet. We'll show you all together. Right? Amplitude is constant. Okay. Right? Okay, I can show it separately. Right? That's your cos graph. That's your A minus A naught sine omega t. Right? As I say, you can differentiate it to get your, right? To show that V equals to minus cos omega t. And then acceleration is just that. But it's not in the syllabus. You're not required to derive all that. Right? I call oscillator the oscillating body. For an oscillating object starting from x equals to 0, the rest position, the and moving in the positive x direction, the displacement time is given by the equation. There's a sine graph. But if it's going starting from 0, starting from maximum, then it's a cos graph. Okay with that? Or we can rewrite it as that. Okay, you can go and
Yeah.
show, you can show it's the same by using your math formula, trigonometry formula. Okay, or you can think of it as the object is, as the oscillator is moving to the right, or in SHM, you can think of a similar particle there moving in circular motion, right? And then this is 0, this is pi, that this one is pi, sorry, this is pi over 2, this is pi, then this is 2 pi. Right? So general equation, don't think you need to go that far. So in this case, if you start from 0, your phi is 0, phase, the phase is 0. But if you start from maximum amplitude and moving to the left, then it's pi over 2. What is the phase of an oscillating particle? Memory word, nothing much. Phase describes the point that an oscillating mass has reached within a complete cycle of oscillation, usually identified as a phase angle. What is meant by phase difference between two oscillating particles? Phase difference between two oscillating particles show how much in terms of radian they are out of step. Right? This is in phase. Two oscillators are oscillating in phase. Both objects oscillate in the same direction, reaching maximum at the same time, minimum at the same time, oscillating with the same frequency. Right? Amplitude doesn't have to be the same. Two oscillators are oscillating in anti-phase or 180 degrees out of phase. If one is moving upwards, at the same time one is moving downwards, right? So this one will reach maximum amplitude, this one will reach minimum amplitude, right? We're just repeating. Okay, question. Why is it good to count the oscillation at the rest position? When you do the simple pendulum experiment, why is it good to count the oscillation at the rest position rather than we always count at the right hand side or left hand side? Why? Applying your name
Uh,
SHM? Yep.
is it because it's easier to
No.
like?
At the rest position, the velocity is the largest, whereas at the other position, the velocity are at the maximum amplitude, velocity is zero, so it's moving very slowly. So you have to count it fast. Okay, now?
Yeah.
Okay, this is a target moving in SHM. Where should you aim your rifle to be sure you hit the target? Explain. This used to come out in objective in under SHM but now no more objective anymore. So where should you point your rifle to make sure that you will hit the target? Same,
Uh,
applying the, yep.
E.
C is where it's moving too fast. So where it's moving too fast, it's unlikely you will hit the target. A or E is where it's moving slowly, either at maximum amplitude zero, right? At A or E, as at this region, the target is moving at either stationary or moving slowly. That is where you're likely to hit it. Okay,
Yeah.
we can show lah. Right? This is for your info lah. Right? Where this tape is moving to the right at constant speed, it represents the time. And this one, we can put a pen or marker at the bottom there. So it oscillates up and down. Can show that the oscillation is sinusoidal curve. Right? Or we can show that this doing a dark room there, strip of film moving at constant speed. This is a ball attached to the reference circle or rotating table. Right? So the projection of the ball on the film will show that it's a sinusoidal curve. Right? Just info only. Just for info only. Right? So the amplitude is the radius of the circle. Right? Distance the ball from the center or radius of the circle. Right? Or this one is taken from Duncan. We can show that as the ball moves in a circle, the shadow move in simple harmonic motion. Right? There's a light source. You do it in the dark room there. Any comment? So in this case, the radius of this ball, right? Radius of this ball from the center is the amplitude of simple harmonic motion. Right? Well, this one show you from the internet. You can. Okay, we won't bother about this. Right? This is just to show that simple harmonic motion and circular motion are equivalent to each other Okay, we won't bother to go over that Not required in your syllabus. Right? Can do the experiment. Right? Same thing. This is your linear track to give you a frictionless surface. This is a glider. Both of the spring are stretched, so we can displace it. Then you move in simple harmonic motion. Okay, so we have completed. Summarize for you what we have done. We completed this part there up to here. Right, next part will be here This part Okay. We haven't done this part yet. Okay, just to summarize for you what we have done, let's do some question. Okay, page 100. These are the equation that you need to know how to use. This one you can review yourself. Try this one.
Page 100, question 4.
What is the spring constant? 1400. Can.
Okay.
What's the load required for the spring to extend to 7 cm?
Uh, yeah, let me calculate.
This is your AS work. Oh. Related, you are expected to know if it's related, but they won't ask you
98.
specific question on what is spring constant. Right? 98 Newton. How to calculate the period? Just use this formula. Lor. They have to give you this formula. Lah. Not required to memorize, but they have to give you the formula. Put in your formula and calculate out. Lor. Okay or not?
Yeah. Hey, teacher,
Yeah.
isn't T for period?
C is for period. Lor. T.
T is period, then frequency is 1 over T, right?
Frequency is one over period. Lor. Correct.
Oh, yeah, you didn't write there.
Here, here we are using, we are calculating mass. Right? We are using this equation to calculate mass. 70 Newton is the weight. Divided by 9.8, not 9.81 to find your mass. Okay.
Yeah.
Right? We calculate the period. Angular frequency. What is angular frequency? 2 pi over t. Lor. Natural frequency, f. Lor. 1 over t, 2.23 per second. Okay.
Yeah.
We should be able to do that. Just to review with you. Calculate the period. Pendulum takes 50 seconds to complete 20 oscillation. Calculate the period.
What? What? 20?
Can
Right. Yeah.
you should be able to do this simple calculation. Any question?
Nope.
Okay, good. Okay, now reading the graph. Displacement of an oscillating object is given by the graph. Below, what's the amplitude? It's taken for internet lah.
The deal is 10.
Okay, 10 cm. Period.
Period 3.
3 seconds. Okay. Frequency.
Frequency 1 over 3.
1 over 3. 0.33 per second. Angular frequency.
Uh,
Right, all this formula must be memorized already. Got 10 more minutes. Right? 2 pi over f or 2 pi over t. Lo. What's the equation of the graph?
Y equals to uh y equals to 10 sine x.
Right? Omega t. Lo. Omega t. Okay.
Omega. Oh yeah, because
Omega t.
okay.
Okay. The displacement of the oscillator is given by the equation in cm. What's the amplitude? Yep. Should be able to read.
Amplitude is 20. 20.
20 cm. No? Angular frequency.
4 pi.
Right? 4 pi. Okay, good.
4 pi.
Period of oscillation.
Period
2 pi over omega. Lo. Okay, no?
yeah.
Maximum amplitude of velocity. Same as circular motion.
This one you use a special formula.
Yeah, R omega, that's all.
Oh yeah, yeah.
Right? Where R stands for amplitude, lor. 20 for 4 pi, 250 cm per second. Okay, displacement at a time of 0.2 second. Yep. What's your answer?
Yeah.
Remember, it's in radian. Substitute, lor. Huh?
0.9.
Huh? 11.8 cm. Lor.
Eh?
In radian, I make sure you convert it to radian.
Oh yeah, yeah, I got it, I got it.
Okay,
Yeah.
sketch a graph. You should be able to sketch a graph. Okay,
Yes.
you calculate already. You should be able to sketch a graph. Lor. Okay, state the equation for defining simple harmonic motion. This is an old partial question.
Um,
Yeah, memory work. 1 mark. There. Okay or not?
minus omega square times x.
Ah, x is displacement. No? A is acceleration. Omega is angular frequency. Right? This is a graph of acceleration against time. Deduce from the numerical value given in the graph the value of this simple harmonic motion of the period. What is the period?
Here is the v omega, right?
No need. Read from the graph only. Yeah,
Oh yeah, yeah, shit.
this
Oh
straightforward.
yeah, zero point 0.4,
Read from the
0.04,
graph.
0.04.
0.04.
Yeah.
Second, frequency.
1 over 0.04.
Hmm. Angular frequency.
That one must use v equals to no v omega, right?
Say again.
Uh, this one is v omega, right?
D omega.
Wait,
This omega, you should be able to
okay.
convert it from period or from frequency to pi f lor,
Oh, 2 by f. Okay.
or to pi over t lor. Either one. Amplitude. Read from the ground lor. What's the amplitude?
2.03.
Amplitude.
Sorry, sorry. Oh, amplitude. Oh, 50, 50.
Remember, the graph is acceleration. So you have to use the definition. No? Yes, that's the reason why they ask you to use definition. They ask you to define because they wanted to use it.
Yeah.
Right? Omega, we have calculated. A is 50 from the graph. Omega square. Then from there, you can calculate your x naught. No? Okay.
Yeah.
Right? Sketch the graph to show how the displacement varies with time. Under 80 degrees out of phase. So remember that acceleration and displacement is 180 degrees out of phase. Like that. Oh? Inverted.
Oh, teacher,
Yep.
teacher.
Can or not?
Whenever there's a whenever there's an acceleration, right, it's always 180-degree out of phase.
180 degrees out of phase with displacement.
If there's an acceleration,
On this equation, they are 180 degrees always directed opposite to each other. There's 180 degrees out of phase, no?
Oh, so it's always
Always,
always.
always, no exception. Okay,
Yeah.
define memory work there, that's all. A tube is sealed at one end, has a total mass of m and uniform cross-sectional area A. The tube floats upright in a liquid of density rho and length L submerged as shown in figure. Okay, right, the tube is displaced vertically and released. The tube oscillates vertically in the liquid. At one time, the displacement x as shown in figure, right? That's the displacement x. You push it down, it oscillates up and down. Right? From the theory, we derive this equation. Explain how it can be deduced from the expression that the tube is moving with simple harmonic motion. Yep. Go to definition. No? That's the reason why they ask you definition. These are all constant. No? So A is proportional to minus x.
Oh yeah.
Okay or not? Okay.
Constant. Okay. Yeah.
Then after that, they will ask you to use the equation. No? The tube of cross-sectional area is floating, cross-sectional area 4.5 cm square is floating in the water density that calculate the mass of the tube that give rise to the oscillating of 1.5 Earths. Comparing with the definition, right, omega square is equals to that one. Right? Omega is 2 pi f. Right? So replace your omega with 2 pi f square and put in your value that's given. Right? Frequency, that's your frequency. Area there, convert from cm to meter square. Density, density, G is 9.81 divided by mass. Okay. Okay, should be cutting off at any time.
Yeah. Okay, teacher. So Thursday we have
I will
two
confirm with
hours.
you.
Okay.
Okay, I think that's the end.
All
Anything you
right.
need to ask?
No.
Okay, then. Thank you.
All right. See you, teacher. Bye bye.
Bye bye.